So, in order to, we'll first look at the diffusion current, okay. So, and we will see why it's called diffusion and where that comes about. So, we're going to make a few assumptions, okay. Without these assumptions the mathematics can get very difficult, and therefore we have to make assumptions in order to look at some answers. These assumptions might sometimes, in general in semiconductor physics, when you make assumptions you always do so in order to get a glance into what the non-equilibrium condition is, okay. It is very hard to calculate the non-equilibrium condition while making zero assumptions, okay. And it is only to get a glance as to into the behavior of the device in non-equilibrium or maybe very close to equilibrium that you make certain assumptions, proceed with the analysis, and develop an understanding on the behavior. So, here the assumptions that we are going to make are the barrier height is much greater than kT. So, the first assumption that we are making is this barrier height q phi b is much greater than kT, okay. The second assumption that we will make is that even though we are applying a voltage and taking the device out of equilibrium, okay, we are applying a voltage taking the device out of equilibrium, yet the carrier concentrations at these two nodes, okay, that is x equal to 0 and x equal to xd have their equilibrium values, okay. That is the second assumption that we will make. They have not changed too much, we are just slightly out of equilibrium, okay. We are just going to take the system slightly out of equilibrium, we are going to apply a very small voltage VA, and we are going to assume that these concentrations do not change from their equilibrium value. And the third assumption we make is that it is a non-degenerate semiconductor. That means that even though it is an n-type material, the doping is not so high that EC minus EF in the bulk is less than 3 kT, okay. So, it is most definitely the case that EC minus EF in the bulk is greater than 3 kT. Alright. So, with these three let us write out a general expression for the current, which is got the drift, it has got the diffusion term, and that is my current density. Now, we are going to make a few substitutions here. Now, this electric field that you see here, we are going to say that the electric field is minus d phi by dx, where phi is the potential, and we substitute minus d phi by dx in terms of in the place of E. The second substitution is that if you think about the diffusion coefficient, we had earlier seen that the diffusion coefficient, when we looked at the derivation of the diffusion equation, we found that the diffusion coefficient was related to the mobility via the Einstein's relation, right, kT mu n by q. We are going to say that this relation holds and your mu n is simply q dn by kT. So, we are going to make this assumption, and instead of mu n we are going to throw in this particular term, and instead of electric field we are going to throw in this particular term, and we will end up with an expression for the current density to be this. So, what we are going to do is we are going to take this expression and we are going to multiply this little factor, which is e to the power minus q phi by kT on both sides, and we are doing this for a certain reason, okay, and it is because you will find that the expression on the right hand side is equal to this term here, okay. So, if you make these changes, if you were to make all these substitutions and multiply this factor, you will end up with seeing the current across the junction, the current density to be equal to this term here. And now this is nothing but your expression for a diffusion current. So, if you imagine that to be some carrier concentration N1, the current is nothing but q dn dn1 by dx, which is nothing but your diffusion term. So, that is why we are talking about the diffusion of carriers across the in a Schottky contact, okay, and phi is my potential. So, there is a potential dependence here. So, with this being the current across the junction, we just need to solve this differential equation. So, you have your j e to the power minus q phi by k t to be equal to this term, and we need to solve this differential equation in order to obtain the current density. So, the current density is simply, if you just integrate on both sides, you take the dx from the denominator, put it on the left side and integrate, and then rewrite the expression, keep j out, you will find that the current density is simply given by this factor here. We had seen that j e to the power minus q phi by k t was equal to q dn d of n times e to the power minus q phi by k t by dx. So, we are taking the dx to the other side. So, we are saying that j e to the power minus q phi by k t into dx is equal to q dn d n e to the power minus q phi by k t, and we now integrate both sides. The j is common, so the j comes out, and this term here, the remaining term, that integral is shifted over down to the denominator, and that is how you end up with this expression. So, the upper integral is easy. So, this is integration from 0 to x d, sorry, that is not very clear, but it is 0 to x d. So, the numerator is quite straightforward, because there are no terms here that depend on this particular factor, and therefore, the numerator is simply q dn into n e to the power minus q phi by k t with the limits going from 0 to x d. The denominator is something we will look at a little later. Okay. So, that is that expression. Now, if you look at the numerator, we are going to apply these limits. So, all we are going to do is we are going to take the n at x d into e to the power minus q phi at x d by k t minus n at x 0 into e to the power minus q phi at x 0 by k t. We are going to apply these limits. Okay. And the denominator has got this term phi. The phi is the potential, and we know that the potential varies as the quadratically with x, right. So, that is the potential. So, that is what you obtain by solving Poisson's equation, assuming the full depletion approximation. So, we are going to substitute that phi. So, because phi is a function of x and that is that function. So, we are going to make that substitution and rename our denominator to this term here. Okay. So, now what we need to do is identify what is the carrier concentration at x d, the potential at x d, the carrier concentration at x equal to 0 and the potential at x equal to 0. And if you identify these 4 terms, you have your numerator. So, the potential at x d, so this is the band bending. We had earlier referenced the potential at x equal to 0 to be 0. So, that was our reference, and at x equal to x d we had our built in potential minus V a, because we have now applied a bias voltage V a. So, it is phi b I minus V a. So, the potential at x d is phi b I minus V a, the potential at 0 is 0. And the charge concentration at x d is the same as we had said, it is going to be the same as the equilibrium concentrations. That is one of the assumptions we have made. Okay. So, the concentration at x d is n c e to the power minus q phi b by k t into e to the power q phi b I by k t. Okay. So, how does that come about? Okay. So, it would have been good to have a band bending diagram here, but we can just draw it. Okay. So, this is the case, right. So, you have your conduction band, that is the Fermi level, okay, and that is q times the barrier height, and that is, let us say, xd, and that is your built in potential minus Va, okay. And your EC minus EF, okay. So, if you look at this term here, EC minus EF, it is the barrier height minus this particular value, okay. So, it is q phi b minus q phi bi if it was the same as equilibrium. So, if this is the equilibrium case, q phi b minus q phi bi is your EC minus EF in the bulk. So, that is basically your EC minus EF at x equal to xt. So, NC into e to the power minus EC minus EF by kT at equilibrium is nothing but NC e to the power minus q phi b by kT into e to the power plus q phi bi by kT, which is basically this term minus this term, and there is a negative sign there, and therefore you end up with this expression. So, that is the carrier concentration at xt in the at xt at equilibrium, and we are going to say that in the non equilibrium case that carrier concentration has not changed much, okay. And at n equal to 0, once again the carrier concentration has not changed much from the equilibrium case, and your EC minus EF remains to be your NC e to the power minus q phi b by kT. So, that is your EC, that is your EF, and that is the difference, which is nothing but your barrier height by kT. So, we now have n at xd, we have n at 0, we have phi at xd and phi at 0, and we now substitute these 4 parameters in your expression. In the previous slide, if you look at the expression here, we have to calculate these 4 parameters. We now have defined all 4 of them. We substitute them, and we will end up with the numerator having a term like this, okay. Now, let us worry about the denominator now. So, that is the numerator. So, that is done, okay. So, now let us look at the denominator, okay. So, there is definitely a typo here, okay. So, that is not complete. So, if you go to the previous slide, if you look at the denominator, you had a term which was e to the power minus q in q square n d by epsilon s into x d x minus x square by 2, the whole thing by kT, all right. So, now we are going to say that if x is really small, because we are talking about regions that are here, okay. So, let us look at x being much less than xd. In those regions I can ignore the term x square by 2, okay, because x dx is much greater than x square by 2. So, I am going to simplify that expression to this term, okay. So, we are going to write, so there is a typo here. So, I am going to rewrite that expression. I am going to say it's 0 to xd e to the power, okay. So, let me just make sure I transfer it correctly, minus q square n d by epsilon s x d x by kT. So, that should be the expression here, okay. And then you perform the integral with respect to x. So, the integral of this term with respect to x, and after you apply the limits will give you this relation that you see here, all right. And if you make one further assumption, that is e to the power minus q square n d by epsilon s x d square by kT is quite small as compared to 1 and you replace this term by 1, you will end up with the current density to be equal to this expression in a shown in the blue box here, wherein you have a big prefactor here. Okay. Now, the key points of this prefactor term are, since it is a diffusion current, definitely there is a dependence on the diffusion coefficient. Okay. There is a significant dependence on the barrier height, which basically means that if the barrier height is very large, the current is going to drop quite a lot. Most interestingly is this dependence on VA. Now, when VA increases, what happens? You will find that as VA increases, you have an exponential dependence on VA. So, if VA increases, so if the bias, if the device goes to forward bias conditions, let us say VA is greater than 0 and it continues to increase, this term is going to shoot up quite significantly, but then you also have a phi bi minus VA. But since it is a square root dependence on phi bi minus VA and an exponential dependence on QVA by KT, this term is going to dominate the current expression and the current will increase. Okay. So, though I have not shown it, it is worthwhile to imagine what the current voltage characteristics looks like. Okay. So, if you forgive this expression or if you sort of ignore this dependence on VA and say that okay, even if VA changes a little, this is not going to change significantly as compared to this particular term. If you go about with that understanding, you can say that J is as though you have a J naught. Of course, it is a light dependence on VA, but as we discussed, you are going to ignore that. J naught e to the power QVA by KT minus 1. So, what does this characteristic look like? Okay. So, if you draw the current voltage characteristics here, you will find that this is the current, that is the voltage, okay, and at VA equal to 0, the current is 0, which makes sense because you do not want to have a current at VA equal to 0, because that would mean it is a current at thermal equilibrium. So, that is VA equal to 0. So, that is the thermal equilibrium point. And then as VA increases, your current goes up quite a bit, it increases exponentially, and when VA is less than 0, the current decays, but not it is not that. So, you have a curve that looks like this. Okay. And therefore, it is a device that allows current to flow in one direction as compared to another. Okay. So, if I were to apply say plus 1 volt and minus 1 volt, I would have a lot more current flowing through the device at plus 1 volt as compared to the current flowing through the device at minus 1 volt. So, you could substitute the values here and you can calculate that. Therefore, it is a device that allows current in one direction and therefore, it behaves like a diode. Okay. So, this is a technical term. We will, I think some of you might be familiar with PN junction diodes, but these devices are something called as the Schottky diode. Okay. And they have a rectifying nature, and that is why it is called as a rectifying contact. And what do you mean by rectifying? Okay. Now, the term rectifying comes from the use of diodes in processing sinusoidal or AC waveforms, but essentially it means that it allows current in one direction, it aids current in one direction and does not permit current in the other direction. So, let us just leave it at that. Okay. So, it is a diode, it is got a rectifying nature. Therefore, if you think of if somebody says a metal semiconductor contact with a rectifying property, then they are talking about the Schottky contact, and it is a Schottky diode. Okay. So, just like you can buy PN junction diodes in a market, you can also buy Schottky diodes, and Schottky diodes have got some very interesting features. Okay. So, the first point is, since we talked about electron transport, okay, So, you have a n type semiconductor and we are talking about the transport of the electrons across the junction. So, we are talking about the majority carriers. So, these diodes are using the majority carriers for charge transport. So, this is a point to remember, and when we discuss p-n junction diodes we will come back to this point. So, Schottky diodes have a current voltage characteristic that is dependent on the majority carriers carrying the current. So, if it is a Schottky diode based on a metal p semiconductor, then it is going to be the holes that are going to be responsible for the current. So, majority carriers are responsible for the current. Okay. So, that is a key point to remember. There are other features that will become more clear when we discuss p-n junction diodes, but this is a key point to remember. So, the built-in potential, okay. So, we will see that when it comes to p-n junction diodes, the built-in potential in a Schottky diode can be made much lower as compared to the built-in potential in a p-n diode, but we will save that point for later. So, this is the derivation of the diffusion current through the Schottky contact. So, just on the few features. So, just to think of it very intuitively, okay. So, why is it that you have this exponential dependence on the voltage? If you think about it in a very intuitive manner, if you just forget the mathematics and you say that I just want a bird's eye view or a very simple understanding of what the diffusion current is. So, you had your equilibrium condition, right. So, let us look at the carrier flux or the current going from the semiconductor to the metal, okay, and the current going from the metal to the semiconductor. So, the current going from the metal to the semiconductor is this, and the current going from the semiconductor to the metal is that. So, this is the current, okay. So, which means that JMS corresponds to the electron transport, electron flux from the semiconductor to the metal, and JSM corresponds to the electron flux from the metal to the semiconductor. So, let us look at the electron flux, okay. So, at equilibrium you have to have these two currents being equal, okay, otherwise you cannot have currents at equilibrium. So, which means that the electrons are trying to cross this barrier phi b from the metal to the semiconductor side, and the electrons from the semiconductor to the metal side are trying to cross this barrier phi bi, which is the built in potential. Now, when we applied a positive bias and these two were equal, okay, so this flux balanced that flux, there was no current. Now, when we applied a positive bias, this barrier became a little bit shallower, okay. So, the built in potential is now phi bi minus Va, okay. So, your Va has changed the barrier height. I am not talking about this side, I am talking about the barrier from the semiconductor to the metal, okay. The Va has changed the barrier seen by the electrons trying to move from the semiconductor to the metal, but the electrons moving from the metal to the semiconductor saw no influence on their barrier height, it is still phi b. And why is it still phi b? Because it is a constant, right. This is nothing but your q phi m minus q chi s, right, it is a constant. So, you can even though we have applied a voltage Va, the metal to the semiconductor current has not changed because the electrons moving from the metal to the semiconductor remain the same. But on the other hand, the electrons coming in from the semiconductor to the metal suddenly see a much lower barrier, and therefore their flux increases dramatically, okay. So, this is the reason that applying a forward bias suddenly allows a lot of electrons to migrate from the semiconductor to the metal, while not having any influence on the flux of electrons from the metal to the semiconductor. So, if a lot of electrons flow from the semiconductor to the metal, it implies that we have established a large current from the metal to the semiconductor. So, if you want to think of this p-n junction, if you want to think of this Schottky junction. So, you have a metal semiconductor contact, that is your positive, that is your negative. it is like as though we have a diode. So, that is a symbol for a diode, and it has got this rectifying or a diode like nature. It allows current in this direction while not permitting too much of current in the opposite direction. Okay, so that's basically a good overview of the current due to diffusion in the junction diode, in the metal semiconductor Schottky junction diode, and these are called as Schottky diodes. So, we will now look at another mechanism, okay, and this mechanism is something called as thermionic emission. Okay. This mechanism too gives you, gives you insights into the rectifying nature of this. It shows you that the Schottky contact behaves like a diode. So, we will see that towards the end of this discussion, this mechanism also supports the diffusion current expression, okay. But it is just that the terms are a little different, okay, and therefore, these two mechanisms are sometimes treated together and under something called as the thermionic diffusion theory. Okay, you can think of both these mechanisms the same, you can model them in a better manner, but we will just talk about the thermionic emission separately. So, what was the thermionic emission? As we discussed, the thermionic emission takes into account all the carriers that have got a high enough velocity or high enough energy. So, you have an electron there, and that has got a high enough energy that it really does not care about the nature of the barrier. Okay. So, it is simply this electron moving from the semiconductor to the metal that is going to create a current from the metal to the semiconductor. So, let us see, let us take a count on the number of electrons and see what their velocity is. So, that should be the approach to calculating the thermionic emission or the thermionic current. So, it is called thermionic because it is temperature dependent, because the velocity of the carrier is dependent, it comes from the temperature. So, let us now define three directions. Okay. So, we need to first define an axis before we talk about all this mathematics. So, let us define this to be the x axis, as we have always been using. We will define the y axis to be, say, out of the plane, okay. So, which I will just draw in this manner, and the z axis is going upward there. Okay. The y and z are interchangeable because you will see that it is really irrelevant as to what you pick as your y and what you pick as your z axis. So, the current we are interested in is basically the flux of the carriers, right. It is essentially NQ into the velocity. So, that is the current. The only thing is this velocity is not because of an applied electric field. Okay. If it was due to the applied electric field, we would call this a drift current, and then it would have been mu into the electric field, but that is not the case. Okay. So, this velocity is simply because of the energy possessed by the carriers, due to which they are sitting well above the conduction band edge. Okay. So, we will just, and we are interested only in the velocity in the x direction. Okay. We really do not care if a carrier sitting on the semiconductor side is moving in the y direction or the z direction, because that is not contributing to the current, because the semiconductor has to cross the junction, I am sorry, the electron has to cross the junction in order to contribute to the current, and therefore, we are only interested in the velocity in the x direction. So, n into q into the velocity in the x direction gives me the current, but I need to sum up all the electrons or the electron count, all the free electrons sitting from EC to infinite. Okay. So, therefore, I need to perform an integral from here to there, and at equilibrium this current is equal to the current from the metal to the semiconductor side. Now, what we will do is we will take this dN, okay, and rewrite it as dN by dE into dE, okay, because we know what dN by dE is. dN by dE is the number of electrons per unit volume per unit energy, right, and that is nothing but the density of states into the Fermi function. So, we will just write dN by dE is equal to the density of states into the Fermi function, and that is the density of states there, and this is the Fermi function here, which is approximated by the Boltzmann's distribution here. Okay. So, we have rewritten 1 by 1 plus e to the power e minus Ef by kT as simply e to the power minus e minus Ef by kT, because we have assumed that this term is greater than 1. Okay, that is the Boltzmann's approximation for f of e. And furthermore, we have split, for the sake of clarity in the analysis, we have split e minus Ef, we have rewritten that term as e minus Ec plus Ec minus Ef, and I have retained this term here and that term there. So, why are we making the splits? So, this is the conduction band edge. We are interested in looking at the velocity in the x direction of all these carriers, and these carriers have got some energy E, okay, have got some energy E, and this energy here is Ec. So, the carrier sitting at Ec has got 0 velocity, and E minus Ec, this gap is especially important for me because that is the energy that is given to the carrier in the form of kinetic energy. Okay, so, that is why we are trying to rewrite E minus Ef as E minus Ec, we are trying to get a gauge on what that energy is, plus Ec minus Ef, where Ec minus Ef are two well known quantities and therefore, it is a constant. Okay. Now, E minus Ec is essentially the kinetic energy of the carriers. So, here we are making an assumption that all the energy of the carriers above the conduction band is the kinetic energy, and we are doing so in order to get a measure of this velocity. Okay. So, E minus Ec is mv square by 2. So, me is the effective mass of the electrons, and here the v is not Vx, Vy or Vz, it is the v vector. Okay. So, if that is your x, y and z, you can think of v as in all three, it has got all three components in it. Okay. So, essentially your v square is Vx square plus Vy square plus Vz square, because that is the way the energy is going to distribute itself. So, E minus Ec is mv square by 2, and if you take the derivative, if you take what is dE by dV, dE by dV is nothing but me v into 2 by 2. So, it is me into v, okay. So, me star into v, and therefore, my dE is nothing but me v into dV. And what we are going to do is now we are going to substitute these two terms, okay, and we are going to try to estimate what that quantity is. So, I am trying to calculate that integral, and and I know my dN by dE is nothing but g into f of e. So, now I have dN by dE into dE, okay, which is basically my dN as nothing but this term here into e to the power Ec minus Ef into all these terms put together. So, you can see that the whole expression is now written out in terms of the velocity of the carriers, which was our goal. We are trying to get an estimate on the velocity. So, now all this is in, you do not see the Vx, Vy, Vz components, because we need to convert this to the Cartesian system. We need to split out the V into these three components. Now, V square is Vx square plus Vy square plus Vz square, and this volume element is simply this volume element here. Okay. So, we now rewrite this expression dN by dE into dE in terms of Vx, Vy and Vz, because now we have a measure of the velocity, but in particular we want to get a measure of the velocity in the x direction, because that is what is going to cross, those are the carriers that are going to cross the junction, and those are the carriers that are going to contribute to the current. Okay. So, that turns out to be, I will not read out this expression, but it turns out to be this big term here. Okay, so here you can see the summation of the 3 components. So that would have been V square by 2 kT. So that is now split into these 3 exponential components. So now we can write out the current expression, right. So the current was nothing but this term here. So that is why we started, and we now have estimated this component in terms of the velocities. So that is what all this all these equations were about. Okay. We wanted to get this entire expression as a function of Vx, and we have done that. Okay. We have got a function of Vx, Vy and Vz. So now we substitute this expression for this quantity here, okay, and we rewrite the integral in this form. Okay. In the y direction, we really do not care about what the velocity is. So we consider all velocities from minus infinite to infinite. Okay. So that is the velocities in either direction. Z direction, we again do not care about what the velocities are, but in the x direction we are only interested in those carriers. So let us say I have a carrier sitting here at the conduction band edge. Let us take another example of a carrier sitting here, and let us take a carrier sitting here. Okay. So let us say we have these 3 carriers which we will call as A, electron B and electron C. Now the velocity of the carrier here, this A, is 0 velocity. Okay. So that is not going to contribute to any thermionic currents. The velocity of carrier B is not 0, but it is still not high enough. It is not going to, it is not something that is going to walk past this barrier without really caring about the barrier. The electron B really depends upon the nature of the barrier and how all this changes and the width of the barrier here, etc., in order to contribute to any current. Okay. So we are not interested in carrier B as well, but carrier C has got enough velocity. Okay. So essentially it is above this dotted line, okay, and it has got enough velocity to just walk past this barrier without really worrying about the nature of the barrier, and that is the essence of the thermionic current. So it is carrier C that we are interested in. So it is only those carriers with a velocity corresponding to this energy level, this dotted line and above, that are going to contribute to any thermionic emission. So we are only interested in those velocities. Okay. So if you think about this entire integral from minus infinite to infinite with everything in there, the everything that is below V min does not contribute any current. So that entire current is essentially 0, and it is only that which has got a minimum velocity of V min and above that is going to contribute to any current. Okay. So it is these carriers at this dotted line are said to have a velocity of V minimum. That is the minimum velocity of the carrier for it to contribute to a thermionic current, and we only consider the integral from that minimum velocity to above. And what is that minimum velocity? So what velocity are we talking about? If the carrier at A has got 0 velocity, it is this energy which corresponds to V minimum. Okay. So V minimum, so if you think about the kinetic energy of the carrier here, mv square mv minimum square by 2 is essentially your phi bi minus Va, it is this. Now here for the first time you see the impact of Va, right. So far we never saw Va appear anywhere, but Va determines what the minimum velocity is. So if my Va is, so let us say that is my equilibrium condition, and if my Va is greater than 0, the requirement for my V minimum has changed, because the carrier here now has got 0 velocity, okay, and I only need a very small amount of energy, because I only need to cross phi bi minus Va in order to achieve the V minimum required to get past the barrier to contribute to thermionic currents. So V minimum is dependent on phi bi minus Va, and we rewrite phi bi minus Va in terms of all these quantities then. Okay, we can rewrite phi bi minus Va in terms of those quantities. So, now how do we perform this integral? So, look at these two terms. Okay, you look at these two terms here. They are an integral of say some minus e to the power minus a x square dx, and I won't use the symbol x. So, let us say something else. So, let us say a alpha square d alpha. Okay, so that's the integral we are talking about. Now, what is integral e to the power minus alpha square d alpha? It is nothing but the Gaussian integral, which is square root of pi. So, I have put a note here, and in fact this note is a bit confusing because I am using x for something else. So, I would not want this to be confusing. So, this x is not related to anything else, it is just to indicate, think of it as a purely mathematical note here. It is just indicate that integral of minus infinite to infinite of e to the power minus x square dx is square root of pi. So, this is something called as a Gaussian integral, and we are going to use that in that, and therefore, we can easily identify these derivatives, these integrals. Okay, so, these two are easily calculated, they are constants, they are independent of Vy. Okay, they are just constants, but this integral is special because this integral is not the Gaussian integral. It has got a Vx into e to the power minus me Vx square by 2k t dVx. Okay, so this integral is going to give you a different answer. So, you solve for these three integrals and you will end up with an expression for the current from the semiconductor to the metal is going to be this term here, and we will find that the current from the semiconductor to the metal is dependent on Va, because the V minimum now requirement is dependent on Va, and therefore, this is the current from the so I should say that this is the electron flux. Okay, so, the electron flux from the semiconductor to the metal depends upon Va, and the electron flux from the metal to the semiconductor does not depend on Va because of this barrier height. Okay, and therefore, the effective current, so electron flux from semiconductor to the metal is the same as the metal to semiconductor current, and this is nothing but the semiconductor to metal current. So, the effective current across the barrier is JMS minus J semiconductor to metal. So, it is this current going from the metal to the semiconductor minus the current coming from the semiconductor to the metal, and that is given by this expression here. So, this is the final expression for the thermionic emission current. So, once again, if you think of all these terms as a constant, okay, so this entire thing, if you say it is J1, okay, the current is J1 e to the power QVA by KT minus 1. Okay, which is again very similar to your diode like behavior which we saw in the case of a diffusion current. The current is going to have a current voltage characteristic that has not changed, but what is different is to look at is the prefactor term. So, here once again another aspect that is common with the diffusion current expression is that the exponential dependence on the barrier height seen from the metal to semiconductor. So, the larger the barrier, larger the cliff, the smaller the current. So, that is also the same. But if you look at the remaining terms, you find that there is a strong dependence on the temperature. So, as the temperature increases, this current goes up dramatically. Okay. So, therefore, there is a very strong dependence on the temperature, and there is a strong dependence on the barrier height and an exponential dependence on the applied voltage, and this prefactor here is something called as a Richardson's coefficient. Okay. So, that is about thermionic emission. So, once again it agrees with the fact that the current has got an exponential dependence on the voltage, and that the metal semiconductor contact behaves like a rectifying contact. So, now let us come to the last bit, which is the current voltage characteristics through the Schottky contact, but via the process of tunneling. So, what do we mean? Okay, so, as I described very briefly, so far we have looked at tunneling through a rectangular barrier. So, right. So, it has always been tunneling through this barrier. The carrier, even though does not have enough energy. Okay, so, let us say this is the potential energy, that is the total energy is E, and despite E being less than V, the carrier is able to get past this barrier and have a non-zero probability on this side. So, that is tunneling, and this essentially is a transport mechanism. The carrier has gone from this side to the other side, okay, with some probability. So, what we need to find out is where is the tunneling. So, if you have your band diagram, let us say that is the conduction band diagram, right. So, the electrons from the semiconductor to the metal will tunnel through this barrier here, okay, and that is the tunneling that we want to what do you say, capture. That is the current that we want to capture. And what we want to do is we want to identify what is the probability of finding an electron at W. Okay, so, what is W? So, the first thing we are going to do is, this is a very difficult potential profile, right. So, this is a quadratic dependence on distance. So, it depends on x square. So, we are going to approximate this to a triangular barrier. Okay, so, this is the approximation we are going to make. We are going to say it is not a rectangular barrier, but at the same time we do not want to use a quadratic barrier. So, we will give it some distance W, and we will say that the tunneling probability is equivalent to the probability of getting the carriers to tunnel across a barrier which has got this triangular shape. So, this is my potential profile, right. So, this is my potential well, if you want to call it. So, that is potential energy, and that is the barrier Q phi b, and let us say at some distance W the potential profile hits 0. So, that is my potential profile, it goes like that, it comes down like that, and it is there. So, that is my potential profile. So, which means that V of x minus E, so all this is offset you know a bit. So, V of x minus E is this potential. So, it is Q phi b into 1 minus x by W. So, that is defining this line here, okay. And therefore, if you remember the tunneling through a rectangular barrier, you found that the probability had an exponential dependence on Vx minus E, on V minus E, right. So, we are going to borrow that idea and say that, you know, if I know the wave function at psi of x, the wave function at psi at x plus dx is simply going to be the wave function at psi of x into e to the power minus square root of 2 m star to v of x minus e by h bar dx. Okay, so that is essentially saying that this can be imagined to be a rectangular barrier of width dx, and I know the wave function, I know the magnitude of the wave function there, and therefore, I can find the wave function here because it has got this dependence. Okay. So, we are going to take an infinitesimal width dx and say that that is a rectangular barrier, and then proceed from there. Now, if you were to now continue this, you know, you take psi of x plus 2 dx is equal to psi of x plus dx into e to the power, so on and so forth, and go all the way till W, you essentially end up with this relation. The relation between the wave function at x equal to 0 and the wave function at x equal to W is simply e to the power the integral from 0 to W of this particular term there. Okay, so one can, if you are familiar with something called as a Beer-Lambert's law when it comes to in optics, when you throw light, let us say light of certain intensity is thrown onto a material, let us say some liquid which is stored in a container, okay, in a transparent container. You throw light on this material and you measure the intensity of light in the other side. You will find that the intensity decays, sort of exponentially with the distance depending upon the absorption coefficient. So, this is a very similar analogy here. So, in some sense the probability is absorbed, okay, and this is the absorption coefficient if you want to think about it that way. Okay. So, what is the probability of finding the electron on the other side? It is, we know that if the wave function is given to us, the probability is simply psi square, okay. So, it is a it is a square of the magnitude of the wave function. So, the probability, the ratio, okay, or if you say, if you create a ratio which is the probability of finding an electron at W versus the probability of finding an electron at 0, it is simply the ratio of psi of W by psi of 0 the whole square, and we already know the relation between psi of W and psi of 0, and therefore this probability is simply this term here. So, this is the probability. So, given n electrons at x equal to 0, if I put n electrons at x equal to 0, there is a probability that n alpha electrons. So, this is my term alpha, right. So, n alpha electrons appear at x equal to W, and that probability is given by this, and we solve this integral and we end up with alpha being equal to this term here, okay. Now, this little coefficient here is it's got the same dimensions as the electric field, okay. So, this is not the electric field in the semiconductor, okay, it is not, it is just phi b by W, and the problem is we have not defined our W very clearly. So, this is in some sense a very, it is a parameter that needs to be modeled very carefully. Phi b is a constant, but our W is arbitrarily chosen, okay. So, we have chosen it in order to get this very nice triangular barrier that through which we have pushed the carriers through, allowed the carriers to tunnel through. So, therefore, we retain all the other parameters, but alpha could be modeled very carefully by modeling this term, this denominator here. So, typically the way, see, if you think about it, you could cancel these two terms and write it as phi b power half, but then we do not know what W is and that cannot really be measured. So, we leave it as this, as some kind of an effective electric field, okay, which needs to be modeled better in order to get a good estimate for alpha. So, this is the probability of these carriers tunneling through, and we could very simply write an expression of of calling the current density as, I am sure these things can be modeled much better, but a simple expression is n q into the velocity, which should normally be the current normally for n carriers, but since only alpha n carriers got across, this would be the current through the metal semiconductor Schottky contact via the process of tunneling, all right. So, with that we will complete our discussions on the current voltage characteristics of Schottky contacts.